Good morning again. And so let's remember where we finished yesterday. So we started talking about the observations so far and how they're going to motivate our investigation into the formation of binary complex objects. And we talked about the discrete individual observations. One thing we haven't talked about yesterday is the rate of observations. And you may have heard numbers like the Ligever collaboration claiming that the rate of binary black hole mergers in the universe is something like 10 to 200 per cubic gigaparsec per year. And the numbers change a little bit depending on, of course, as you get more and more data, the rate uncertainty shrinks, but it's somewhere in this ballpark. For our purposes, it's close enough. And okay, those are nice numbers. What do they mean? I mean, is 10 per gigaparsec per year a lot, a little? How common or rare is this really? So I think we need to first understand a little bit about how to convert these numbers into something we can actually meaningfully think about to try to get some idea of how significant these numbers are, right? I mean, a gigaparsec seems like a pretty big distance, but how many galaxies are in a volume of a cubic gigaparsec, for instance, right? We need to have some way of comprehending these numbers in some meaningful way. So here's one way of at least trying to do it. So let's first try to figure out, for example, in the same units, what would be the rate of core collapse supernova. So what do I mean by core collapse supernova? So people may have heard that supernovae are often described by some funny letters and numbers, right? So you have your type 1As, your type 2Ps, your type 1BCs, etc., etc. Okay. Core collapse is everything except for type 1A. So the supernova nomenclature is a little bit funny. Type 1A is the weird guy. Type 1A is white dwarf going above Chandrasekhar limit and exploding. How this happens is a separate story. There are two possible channels that people have discussed, either a double degenerate type 1A, where you have two white dwarfs coming together, merging, and leading to an explosion, or a single degenerate channel where you have mass transfer from a non-degenerate star, let's say a red giant, onto the white dwarf. But okay, that's not relevant for our purposes. Those are your type 1As. Everything else, so type 1, B or C, or type 2 of any variety, these are all core collapse supernova. They all leave behind a neutron star or a black hole. So this is a massive star that gets too massive to be supported by, basically it continues its fusion for sufficiently long to typically make an iron core, and then ultimately collapses into a neutron star or a black hole, possibly with some explosion. Possibly the explosion sheds some of the mass, possibly it gives it some kind of a natal kick, so that the remnant is moving because there is some asymmetric explosion of the material. Okay, these are all details, but all of them are core collapse supernova, and the reason they are distinguished is because of their light curves and primarily their spectra. So for example, type 1BC typically do not have hydrogen in the spectra. No hydrogen, whereas type 2 typically have some hydrogen or a lot of hydrogen. Why is this relevant? Well, it's relevant because As we'll discuss later, oftentimes binary evolution is going to remove hydrogen, strip off the hydrogen envelope from the star, and so type 1 BCs are likely to be associated with formation in a binary. Because if you, normal star has hydrogen on the outside, even when by the time it has formed an iron core, typically you're still going to have some hydrogen on the outside because all the fusion is happening in the core, and the outside is just going to be a hydrogen envelope. It's not going anywhere. But if you have a stellar companion, then you can think of it as a kind of tidal stripping of that star by its companion. So you remove the hydrogen, and then by the time the object goes supernova, there is no hydrogen left. It's been pulled off by the companion, so you get a type 1 BC. So for example, for binary evolution, this distinction between type 1 BCs and type 2s is an important distinction. There are a few other special cases, such as, we talked already about parent stability supernova. We might mention either later today or tomorrow electron capture supernova when we talk about neutron star formation. But fundamentally, these are the core collapse supernova. So let's think about what their rates might be. So let's just first think about their rate in the Milky Way, because we kind of know what the rate is in the Milky Way observationally, so we might at least try to see if we can get at the right answer. And it turns out it's not so difficult to get at the right answer for the Milky Way. I won't do all of the algebra, but all you basically have to do is you say, okay, well, I know the current star formation rate in the Milky Way. So this is the star formation rate, let's say in Milky Way. And it's remarkable if we don't know what it is. You might think that we would, the one thing we should know very well is how many stars are forming in the Milky Way, or what is the rate of star formation in the Milky Way. We don't know it very well, but it's maybe about 2 solar masses per year. I've seen numbers ranging from 1 to 7 solar masses per year for the current Milky Way star formation rate. We genuinely don't know it within a factor of a few, but this is not a crazy number. And then you say, okay, well, we have some initial, yes? So, in general, one of the ways to do that, right, is that, of course, very small stars are actually quite difficult to observe, right? You're not, even throughout the Milky Way, necessarily going to be able to see your young 0.1 solar mass stars. For that matter, they take quite a while to even become stars as such. They spend a lot of time in the pre-main sequence phase. So it's easier to look for massive stars. For massive stars, typically you have much more complete surveys, and then extrapolate if you know, at least for some star forming regions where you look at them very closely, you know what the initial mass function is. You can extrapolate it down to lower masses, but in general, people look at again, sort of spectral signatures of star formation. So for example, more massive stars are going to give you an excess of blue light, typically. So massive stars are blue, they're hot. Low mass stars are cooler and redder. I mean, depends on where you're looking. So for example, out to distances of the Magellanic Clouds. So we're now talking, the Milky Way is about sort of, typical scales, just to get a rough idea of how big things are. We're about 10 kiloparsecs away from the center of the Milky Way, 8 kiloparsecs to be more precise. So that's to Sagittarius A star, the massive black hole in the center of our galaxy, right? We have this 4 million solar mass black hole. We're about 8 kiloparsecs away from it. So think of the Milky Way as a kind of a 10 kiloparsec size object, roughly speaking. The Magellanic Clouds are about, let's say, 100 kiloparsecs away, a little bit less, but close enough. The closest Milky Way, roughly Milky Way sized galaxy is Andromeda, M31. That's about 1 megaparsec away. The closest big galactic cluster is the Virgo cluster. It's about 20 megaparsecs away. The scale on which you can basically say, cosmology works. By cosmology, I mean the assumptions that the universe is roughly isotropic and homogeneous work is between 50 and 100 megaparsecs, right? So on much smaller scales, we have the significant local overdensity of galaxies, right? Not surprising, we are not born in a void, right? This is just the anthropic principle that we're going to be where there's an overabundance of matter. So if, for example, you ask, okay, how far can you see stars being born? If you look at the Magellan clouds, which are about 100 kiloparsecs away, with a good survey, you can be sensitive to you can be complete to all stars above about 15 solar masses, right? So within the Milky Way, things are actually funnily more problematic because you have a lot of dust in the Milky Way, so looking inside the galactic disk is actually a problem. There's a lot of obscuration from other things going on. Dust tends to redden things. Young stars are red. They're hard to tell apart. So you might, I don't know off the top of my head the limit on how complete you would be if you try to survey the entire disk, but I suspect it's actually pretty poor. So you're not going to be very good at observing young stars forming throughout the Milky Way disk. Yes? So you're absolutely right. The trouble, so one of the troubles with using overall, and this is one of the things people use indeed, is sort of the bulk spectrum of the galaxy to try to figure out what is going on in the galaxy. But the challenge there is that requires you to have a very good model, well-calibrated model, and it's not actually completely clear that we have the perfect set of models. So for example, recently there was a nice paper by Elizabeth Stanway and J.J. Eldridge, which has argued that a lot of the models for doing this can significantly mislead you in understanding the star formation rate in the galaxy because they didn't account for binaries. And in binaries, because you have some stripping of one companion by the other, you have some mass transfer, etc., it can very significantly change the spectral profile. And so not accounting for binaries in your models is going to lead you to a misjudgment about the stellar population. But overall, you're absolutely right, and this is, for example, how, I mean, of course, remember also this is involved not just with the types of stars you have in the galaxy, but also with their ages, right? Because as stars age, the spectrum changes, right? So for instance, the low mass red stars stay low mass red stars for a very long time, but the massive blue stars evolve and become compact objects in as little as a few million years. For the most massive stars, it's a couple of million years before they end up making a black hole. So the spectrum will change over time, and that's obviously another complication, that you're trying to judge the star formation history along with the stellar mass distribution, and this is inevitably a problem when you're trying to figure out, for example, what is the initial mass function and the mass distribution in any galaxy. I think there was another comment. No? Okay, I was wrong. Okay, so we think it's a few solar masses per year in the Milky Way, and then we can of course say, okay, well, we know what the or we think we know what the initial mass function is, and the initial mass function according to Krupa is something like P of m, and when I write P of m, this is a normalized probability by mass, so Krupa initial mass function, IMF. P of m is a normalized probability by mass, so this is something like 1 over n times dn by dm. By the way, notice one thing, that when you write a probability density function, it actually has dimensions, right? It has dimensions of 1 over mass. This is something that people often forget. But this goes as something like m to the minus 0.3 for m is less than about 0.08 solar masses, m to the minus 1.3 for m between, I think, about 0.5 and 0.08 solar masses, and m to the minus 2.3 for massive stars, m larger than about 0.5 solar masses. So if I now have this mass distribution, of course, okay, I need to normalize it. I normalize it by, these are all proportionality constants, so of course I need to put first of all, a different proportionality constant here, which is just set by the fact that I don't want my mass distribution to have any kinks in it or any abrupt jumps. I mean, it will have kinks. These are different power law slopes, but it won't have any abrupt jumps. But then I, of course, want to normalize it overall so that my integral over all masses ends up being 1. And that then I can compute, for example, the total the fraction of all stars, let's say, above a given mass, right? So if I know my overall mass distribution, I can say that fraction of stars with a mass greater than 8 solar masses, which I can take as the rough threshold for a core collapse supernova. This is just the integral of P of m dm from 8 solar masses to infinity. And if I do this, I find that for a rate of about 2 solar masses per year, I might get something like 1 core collapse supernova per century, maybe 1 per 50 years, which is consistent. I actually haven't checked it for this exact rate, so I should go and check it, but it's consistent with the observations, right? We think that this is roughly how often core collapse supernova actually happen in a galaxy like the Milky Way. So you end up with roughly 1 core collapse supernova per century in Milky Way. Yes, of course. So the initial mass function is, I think you can, it's almost universal as far as we know, indeed. The star formation rate is very different in different galaxies. In particular, the specific star formation rate. So the star formation rate per unit existing mass is very different in different galaxies. So large red elliptical galaxies sometimes are called red and dead galaxies because they have very little star formation rate per unit mass. They have a lot of stellar mass, but very little star formation. There are some younger galaxies, like, for instance, the Magellanic Clouds, that have a lot more star formation per unit mass. In fact, there seems to be some kind of a feedback that people are still trying to understand, whereby at some point galaxies just tend to shut off their star formation, right? So they grow to a certain point and they say, okay, we're big enough, we're not going to grow anymore, so people are still arguing whether that's due to the input from the star formation itself, or for the input from some kind of an AGN heating, because the black hole is also growing during this time, and the black hole gets too massive, produces too much radiation that heats up the gas. It's impossible for hot gas to collapse and form stars. So these are still open questions. Exactly what is the quenching mechanism for star formation? There also, it may be that quenching actually has more to do with, for example, where these galaxies are in their local galaxy group or galaxy cluster. So, for example, if the galaxy gets very large, it's likely to sink towards the center of the cluster. But in the center of the cluster, there's a lot of ram pressure stripping by interaction with other nearby galaxies, and maybe that's what's removing or quenching some of the star formation. So that's still an open question. But yes, the star formation rate is very much galaxy dependent. The initial mass function, as far as we know, is pretty close to universal. Okay, so we now have said what is the core collapse supernova rate in the Milky Way. Okay, now, okay, we still want to convert to those units. So the number to remember is the Milky Way density is such that you have roughly 1 Milky Way per 100 cubic megaparsecs. So that means 10 to the 7 Milky Ways per cubic gigaparsec. And if you have roughly 1 core collapse supernova in a Milky Way per century, so that 10 to the 7 becomes 10 to the 5. And so you might find that you have a core collapse supernova rate of about 10 to the 5 core collapse supernova per gigaparsec cubed per year. But that's all the core collapse supernova. Let's say that we are interested in only the ones that form black holes. Okay, just by way of illustration of how you can use the IMF to very quickly make these kinds of estimates, right? We're only interested in the ones that form black holes. So, you know, we want to know how does this compare with the rate of formation of black holes. Questions? No? Okay. So, oh, sorry. I said that there's a, okay, so this is just an observational statement. There is 1 Milky Way per 100 cubic megaparsecs. So I wanted to convert this into cubic gigaparsecs. So a cubic gigaparsec is 10 to the 9 cubic megaparsecs. And if there is 1 per 100 cubic megaparsecs, there are 10 to the 7 per cubic gigaparsec. Right, so 10 to the 9 divided by 100. Yeah, so that's 10 to the 7, and then there's 1 per century in the Milky Way, so I divide by, okay, century is 100 years, so I divide by another 100, and that's how I end up with 10 to the 5. So, so now what I want to do is, okay, I want to say, okay, but surely many of these core collapse supernova are neutron star forming, not black hole forming, for the obvious reason that black hole, okay, I'm going to assume that things with a mass between, let's draw it like this. I'll draw it. So here's the initial mass. I'm going to write it as mass at 0 age in the main sequence in solar masses. Things that are 8 solar mass. That's not a very good 8, is it? Things that are 8 solar masses or below end up making white dwarfs, if they ever get there. For something like the mass of the sun, you need to wait for roughly the age of the universe for it to make a white dwarf, right? You know, the sun spends close to 10 billion years on the main sequence. So the cutoff mass, sort of for the first stars, is something like 0.9 solar masses. If they were born with a mass of less than 0.9 solar masses, even when the universe is very young, they're still just sitting there as 0.9 solar mass stars. If they were born with a larger mass, they have evolved by now and ended up in one of 3 categories. Either if they were in isolation, if they were less than 8 solar masses, they end up making a white dwarf. If they're between 8 and 20 solar masses, they make a neutron star. And if they're more than 20 solar masses, they make a black hole. Remember, these are very rough, especially this boundary here is you know, very sensitive to possibly even some random stochastic processes that drive the explosion and the formation of instabilities. This boundary here is also possible to shift a bit due to so-called electron capture supernova. which we might mention later if there's time. Also, this is only true for single stars. If you have binaries, you can move these boundaries because you can transfer mass from one star to another, and therefore, you might start with a 5 solar mass star, but you transfer enough mass onto it while it's still in the main sequence that it begins to behave like a 9 solar mass star, and ends up making a neutron star, even though you would have expected it to make a white dwarf. So, these things are crude, but they're at least ballpark estimates that might help you understand the relative fraction of neutron stars to black holes. So how do we estimate these relative fractions? Well, we go back to our very convenient IMF that's written over here. And we say that number of black holes divided by number of neutron stars. This is the integral of m to the minus 2.3 dm from 20 solar masses to infinity divided by the same integral from 8 to 20 solar masses. Notice I don't care about normalization because normalization is going to drop out. So whatever the normalizing constant is isn't relevant. So this is just m to the minus 1.3. Or I can write this m over m dot to the minus 1.3 going from 20 to infinity divided by m over m dot, mo dot to the minus 1.3 going from 8 to 20. And very roughly speaking, I can just approximate this as 8 divided by 20 to the power 1.3. So this is about 2.5, 1 over 2.5 to the power 1.3. So that's about, give or take a quarter. So there are about 4 times as many neutron stars as black holes in the universe. Yes? Yes. Sure. So there are a couple of things that can happen, right? So one is, even if you consider single stars, the composition. So this is running ahead a little bit, but the composition of the star matters because stars tend to lose mass in winds depending on the stellar metallicity. So so we're moving forward a little bit, but it's a good question, so it's worth doing that. So what is metallicity? So metallicity, you have to keep in mind that astronomers' counting skills are about the same as of my daughter when she was 3 years old. It goes 1, 2, many. Sometimes my daughter would go 1, 2, and instead of many, she would say 3. So this is 3, this is 3, this is 3, they're all 3. Okay? So that's exactly what astronomers do. There is hydrogen, there is helium, and there are metals. Everything that's not a hydrogen and helium is a metal. Oxygen is a metal, carbon is a metal, iron is a metal, it's all metals. There is this notion of metallicity, which is what is the fraction of the gas forming the star that is not hydrogen and helium. This is relevant for several reasons. Okay, the first one is that basically in the Big Bang nucleosynthesis, you more or less make just hydrogen and helium. You make very negligible amounts of other things like lithium. but it's almost all hydrogen and helium, and it's very roughly 75% hydrogen and 25% helium by mass. So the first generation of stars, metal-free or very metal-poor stars, sometimes they're called population 3 stars, they are basically all hydrogen and helium. Future generations of stars, they are enriched by the fusion products from the first generation of stars. Because as the star, for example, explodes in a supernova, of course the star has produced carbon and oxygen and so on and so forth, and those things are spewed out into the interstellar medium, and the interstellar medium is enriched with these nuclear fusion products, and the next star that's going to form nearby is now forming out of this enriched gas. So for one thing, the fraction of metals in a star tells you something about how many generations of star formation have happened in this neighborhood. So for instance, the solar neighborhood has a metallicity of about 0.02, so meaning 2% of the sun at birth is metals. It's not hydrogen or helium, and that's actually about as high as things get in the universe. You know, it might be 0.03, but it rarely gets much higher. So even after all of the star formation, the universe is still, the continuing star forming gas is still mostly hydrogen and helium. But there is one other place where this is very important. Metals are hugely important for determining the rate of mass loss in stellar winds. And the reason is, okay, again, this is a huge oversimplification, but it's basically because metals have a lot more transition lines. So if you think of a star that is, radiation is propagating out of the star, if you just imagine, for example, there was just some already thermalized radiation, right? It's just black body radiation coming out of the star. You would expect that most of those photons are not going to be efficiently captured by your hydrogen and helium atoms because they only have a small distinct number of transition lines, right? You know, you have the Balmer series and the Paschen series and so on, right? But you know, there is a limited number of transition lines available to you. In a metal like iron, which has this complicated valence shell structure, you can capture a lot more of those photons. So you can take this radiation coming out of the star and transfer it to an outward momentum of the atoms making up the star. Now, it doesn't mean necessarily just those metal elements, just the iron is going to be pushed out, because of course, once a big iron atom is given some outward velocity where it captures the momentum from an outgoing photon, this iron atom is going to run into a hydrogen atom. The hydrogen atom is light, and it's more likely the hydrogen atom, in fact, that will bounce out, and the iron atom will stick behind. But this very efficiently enhances the mass loss rate. So if you think about the sun, well, okay, even if you know nothing about the stellar winds from the sun, I think it's pretty safe to say that we can put a pretty strong upper limit on the stellar winds from the sun, right? We've just said that the sun is going to live for about 10 billion years, and it has a mass of 1 solar mass, so it really cannot be losing more than 1 solar mass in 10 billion years on average. Otherwise, there wouldn't be anything left of it. So we know that the star's mass loss rate is less than 10 to the minus 10 solar masses per year. It's actually significantly less than that, right? But we know that already, just from first principles, that it has to be less than 10 to the minus 10 solar masses per year. For some massive stars, okay, things are also held by the fact that they have a much higher luminosity, of course, but you might be talking about, in specific phases of their evolution, mass loss rates of perhaps 10 to the minus 4 solar masses per year, in some cases maybe as high as a solar mass per century, right? So we're talking 10 to the 8 orders of magnitude, 10 to the 10 orders of magnitude more mass loss than from the sun, and this is particularly bad in the case of high metallicity stars which have lots of iron. So the mass loss rate is a very strong function of metallicity. Why am I bringing this up? Because if you have a very low mass, a very low metallicity star, then indeed you might expect that the mass of the star is not changing much during its evolution. If you have a very high metallicity star, then you expect that its mass is going to be dropping just because of mass loss well before it gets to exploding in a supernova. Due to winds, exactly, due to stellar winds. That's exactly right. And so that's one of the complications that you're alluding to, and that, of course, can shift this boundary around. Turns out that it's mostly an issue for the highest mass stars. It's the stars in here that really lose tremendous amounts of mass. You know, stars over here, like this boundary won't actually shift very much because, you know, 8 solar mass stars aren't so luminous that they lose, they're likely to lose a very high fraction of their mass through winds, but certainly that's true out here. And as we said before, you know, this boundary is kind of a fluid boundary because, you know, there things over here might make a black hole and things over here might make a neutron star, even if you didn't worry about winds. And this just has to do with the randomness of the supernova process. But this is reasonable on maybe a couple of grounds. There's some observational evidence that this is actually roughly where the boundary lies. There's also a pretty good modeling evidence that this is roughly where the boundary lies. And so I think for our purposes, it's probably safe to make this simplifying assumption that it's roughly at around 8 solar masses and 20 solar masses are where the two boundaries are. That's exactly right. So So these are the only ones that are standard candles. So type 1As are standard candles. Exactly. Yes, but type 1As are actually the ones I don't care about for this purpose, right? Type 1As don't leave behind compact objects. Type 1As, everything explodes. So basically, okay, you can there are two different questions, right? One is how the star evolves up to the moment of supernova, up to the moment of core collapse, and the second, what happens during the core collapse. So during the up to the moment of core collapse, okay, this is largely okay. This was our whole winds discussion, and then during the core collapse supernova, you're absolutely right that of course there are different the light curves of supernova, the explosions are very different, right? They depend a lot, for instance, on whether you still have your envelope on the star or don't have an envelope. Yes, please. Of course. Yeah, so absolutely. So you have to worry about, yeah. Indeed. I mean, there is so there are a few hints we have observationally. So one of the observational hints is that okay, if you make a neutron star, you have a successful explosion. Black holes, certainly at the high mass end, likely you have a complete fallback and not much of an explosion. Low mass end, you may still have at least a partial explosion. But one of the things that, you know, there are some observational hints, for example, of stars that are very evolved giants where we have a guess that their masses are, let's say 25 solar masses, and then they just they just disappear. So the fact that they just disappear says without a supernova explosion, right? So there are people like, oh God, the name has just escaped me, from Ohio State. Oh, okay, this is embarrassing. Okay, it'll come back to me. But anyway, there are people who are trying to do surveys of Chris Kuchanek. Sorry, there are people who try to do surveys of these, for example, of things that look like they're about to go supernova, in the hope that some of them will, and are looking at, okay, do these things actually go supernova, or do they disappear? And if they disappear, that means it's a failed supernova, so it's probably a case of complete fallback onto a black hole. And the observational evidence is maybe indeed that might happen somewhere between 20 and 30 solar masses, but you might still, the things that are 20 solar masses might still make black holes, even if that complete fallback boundary is at 30 solar masses, just because you might still have a partial explosion for the low mass black holes. Sorry, Marianne, please. Indeed. And so there are, you can look, for example, at, okay, if you're interested in the modeling work, you can look at papers by people like Thomas Janka, for instance, where they, you see this sort of almost fence. So it's not a clear divide, but instead you see that there are, some black holes that form here and some neutron stars that form here, and it really depends on the details of a particular model. People have tried to come up with ways to explain what is sort of the critical thing that determines whether or not you have a successful explosion or not, whether the shock can successfully propagate outwards and lead to an ejection of material. So one of these parameters is, for example, the compactness parameter of the core. So how Indeed. So these are, but even the compactness parameter, for example, is a it's kind of a proxy that people try to use to say, okay, well, if you're a stellar modeler, at the end of your stellar model, that's something you can measure. What is the compactness parameter of your core? So here's a hint: if you aren't going to do 3D supernova simulations, will your star explode or not? But all of these things are still very uncertain, as Marianne has said. Okay. So, but now what we've said is that the roughly speaking, the fraction of the rate, let's say black holes make up, 20%, 25% of these core collapse supernovas. So maybe you actually form black hole formation rate is perhaps something like, okay, so I said 10 to the, I've erased it now, but I said that there might be 10 to the 5 supernova, core collapse supernova in total per cubic gigaparsec per year. Maybe the black hole formation rate is 2 times 10 to the 4 per gigaparsec cube per year. Now, why am I writing this down? Well, I'm writing this down in part to compare it with this number, right? So this number is still at least 2 or 3 orders of magnitude smaller than the black hole formation rate. So that's telling you that binary mergers of black holes are still a fairly rare channel. Now that's an important statement, right? Because you might, the question you might ask yourself is, okay, before yesterday I told you that it's very hard to make merging complex logic binaries. Now I'm going to try to tell you that, well, you can make them, but I'm not going to pretend that it's easy to make them. It's still hard to make them, which is why only a small fraction of all of your black holes are going to make merging binary black holes. So if you are going to argue, as some people rightly have done, that some of the processes I will describe now are a little bit fine-tuned, well, up to a point that's okay, because I'm trying to reproduce an obviously rare channel, something that happens to maybe 1 in 100 to 1 in 1,000 black holes. Okay, so I hope that that argument is clear. Okay, so now let's actually talk about the channels. And I'm going to identify 3 key channels and then discuss a little bit, some ways to, let's say, mix these channels, because it's not quite a one or the other thing. Of course, you can have multiple channels contributing at the same time. And even for a single binary, you might have multiple things at play. So channel number 1 says something like the following. We start out with 2 stars that are quite far apart. Those 2 stars, and by far apart I mean, let's say several astronomical units apart. Remember that we said yesterday that you need these stars to be, if you're going to form 2 black holes and merge in the edge of the universe, okay, if we're sort of solar mass stars, you would need them to be roughly a solar radius apart. Now, of course, if we're talking about the progenitors of GW 150914, for example, the 30 plus 30 solar mass binary black hole, okay, those are more massive. You'll remember that the gravitational wave merger timescale went as mass to the -3 times a to the 4th, right? So tau GW was proportional to m to the -3 a to the 4th. And so that means that for a 30 plus 30 binary black hole, 30 plus 30 solar mass binary black hole, A initial has to be less than about 50 solar radii, or about 1/4 of an AU, in order to merge in the age of the universe. It's just the same calculation I did yesterday, but scaling to account for the fact that we're talking about 30 plus 30 solar mass black holes, not a third plus a third solar mass black holes. Okay, I'm not going to bother writing it out, but it's simply the scaling law, right? So you can be, if my mass increases by a factor of 100 from a third to 30 solar masses, then my A can also increase by a factor of 100 to the 3/4 power. So that's how I get to something like 50 solar radii. But remember, this is still 1/4 of an AU, and now I'm talking about a separation that maybe is initially 10 AU, 10 astronomical units. Then this star, let's call this star the more massive one. So I'll draw sometimes astronomers call it the primary and a secondary. So the primary star is a more massive. The more massive star evolves more quickly. And remember, we said yesterday that once the star reaches the end of its main sequence, it's going to expand. And as it expands, it transfers mass onto its companion. So here's my expanded star, and it starts to transfer mass onto its companion. The star hasn't actually moved in. It has in fact moved slightly out, perhaps, when doing that. We'll get back to which way it moves in a moment. But they're still quite far apart. Eventually, this one collapses into a black hole. Then this one starts to expand and transfer mass towards the black hole. And then I'm going to wave a magic wand and say that there's going to be something that happens here which is going to bring them very close together. Just at the right time of its evolution, where this star is no longer a giant, but only the little, very compact core of the giant left behind. So something magical happens. We'll get back to what the something magical thing is. And then you end up with 2 black holes that are quite close together and that can merge within the age of the universe. So that's channel 1. This magical thing, which I will describe in a moment, is called a common envelope. And so this is the classical isolated binary evolution through a common envelope phase. This is something that people have been talking about since the 1970s. Option 2, I started two stars very close together. So they're almost in contact already at birth. Now you might say, well, this is a problem because yesterday you mentioned that stars tend to expand by factors of 100, maybe even 1,000 during their evolution. So if they're already almost in contact, you're just going to end up with a merger of two stars, not two compact objects. Well, here I wave a magic wand that says, abracadabra, stars, thou shalt not expand. And for whatever magical reason, they listen to me and don't expand. So if they don't expand, great. They just evolve into black holes in place. So you have two black holes right here, and these are by construction close enough. And this gives you a eventually a merger within the age of the universe. And this we're going to call chemically homogeneous evolution. And this is something that, in the context of merging binary black holes, chemical homogeneous evolution was something that was discussed long before, but in the context of merging binary black holes, there were sort of two papers that came out almost simultaneously. They proposed it in early 2016, I think. One by Pablo Marchand and collaborators, and one by Selma Demink and myself. And then the third option is the black hole matchmaking club. So you have a bunch of stars sitting all around. Some of them end up making black holes. Others are just normal stars. They end up making black holes without you worrying about, are they too close to anything, etc. I mean, these are not stars necessarily in binaries. These are just stars, floating around in space, right? So they have plenty of room to expand, contract, do whatever they want to, make a black hole. Of course, these black holes are all very far apart and would never merge, but then somehow you persuade the other stars to act as kind of introducers. They arrange for the black holes to meet each other, and ultimately you end up with two black holes that are in a tight binary and that end up merging, and this is called dynamical formation, because you rely on the dynamics of this dense stellar environment to encourage binary black hole mergers. Okay, so these are the three main channels. Isolated binary evolution through a common envelope phase. Isolated binary evolution. So by isolated, I mean not interacting dynamically with any other objects. Isolated binary evolution via common envelope, chemically homogeneous evolution, and dynamical formation. Yes? Okay, so so I haven't even explained what the common envelope is. You're absolutely right that there are some issues with looking for it, so we'll definitely talk about all three of them in detail. So let's start with, since the question was about this one, let's start with this one first. Anyway, it's the one that people have been talking about for the longest, so it deserves pride of place. Yes, please. Sorry, so 1A do not form compact objects. 1A lead to a complete explosion, right? So you drive, you basically increase the mass of the white dwarf too rapidly, and it completely explodes. There is nothing left behind, right? So no compact objects. So you can get compact objects either through type 1 BC supernova or type 2 supernova. Those are the core collapse supernova. So that means the core of at least the core of the star collapses. Now what happens to the envelope? The outer parts of the star, okay, that's a separate question. Some of it might be expelled. Some of it might end up falling back onto the black hole. Okay, that we can return to later. Sure. So observationally we know that type 1 BCs make up actually it's kind of hard to distinguish them. So the 1b and 1c, um, their distinction is whether or not there is helium in the spectrum, and helium is a little bit tricky sometimes to, the amount of helium can be tricky to accurately measure, so people argue about whether a given supernova is quantified as a 1b or 1c, but roughly speaking, 1bc's make up about a quarter of all core collapse supernova. No, sorry. I mean that no. You actually have helium emission lines in the spectrum. Yes. Yeah. Okay. So yeah. So the idea would be if you don't have helium, it means that the progenitor was stripped so much that not just the hydrogen envelope, but also the helium has been removed before the supernova. Okay. So let's. I'm going to erase this. And let's talk in a bit more detail about this isolated binary evolution channel. Now, okay, again, just to, I've said this before several times, but just to draw this picture again, you have a star, you have the core of a star. In the core of a star, hydrogen is fusing into helium. At some point, as the star ages, you end up with a star which is mostly hydrogen out here, and mostly helium in the core. The ignition temperature for helium is quite a bit higher than for hydrogen. So the moment, if you just leave the star as is, there is no helium fusion yet. There is no input of energy. There is insufficient thermal pressure support in the core. So the core begins to contract. The envelope begins to expand. You're releasing binding energy by contracting the core. This energy goes into the envelope. The envelope begins to expand. At some point, you start hydrogen shell fusion. So there's a little shell around the core where hydrogen begins to fuse into helium. That is an extra energy reservoir and leads to even more expansion of the envelope. So your star becomes, this is not drawn to scale because your star becomes a giant at this point and could have a radius about a factor of 100 to 1,000 larger than the initial star. Then, of course, at some point, the core, as it's contracting, it says, okay, I've contracted enough, the pressure gets high enough, the temperature gets high enough that I've reached the activation energy, if you wish, for helium fusion. And so you start fusing helium, and the process continues. So you fuse helium and make carbon, oxygen, neon, magnesium, silicon, iron through a chain of nuclear reactions, which we're not going to discuss here. And at some point during this process, your star might say, okay, enough, I'm not sufficiently massive to start the next process of fusion. So for example, our sun will never even start fusing helium. It will never reach a temperature high enough in the core to fuse helium, so it will end up making a helium white dwarf. More massive stars might make carbon oxygen white dwarfs because they succeed in fusing helium into carbon and oxygen, but then say, okay, my mass isn't high enough, I cannot build up a high enough temperature and pressure in the core to fuse carbon and oxygen, and this process can continue all the way to sort of oxygen, neon, magnesium white dwarfs, things that are massive enough and go on to fuse oxygen, neon, magnesium. Okay, at that point it proceeds all the way to fusing things into iron, forming an iron core, and eventually a classical iron core collapse supernova. So remember, here the star significantly expands. Now, one thing that's worth noting is this core is actually quite compact. So if you remove the envelope somehow, and by the way, there are a couple of different ways of removing the envelope. One is by pulling off the envelope through the tidal field of the companion. Another way is that if you have sufficiently strong winds, you might just eject the entire envelope over time. This core over here, this helium core, for example, is a Wolf-Rayet star. So that's basically a naked helium star. And here we're talking about radii of only 1 or 2 solar radii. So you might have, if we're talking about, let's say, a 100 solar mass star, at this stage, its radius might be something like, let's see, 25 solar radii. At the end of the main sequence, it might be about 100 solar radii. At the end of the main sequence, might be 100 solar radii. At this point, its radius might be 10 astronomical units or 2,000 solar radii. But the core is only 1 or 2 solar radii. So what happens when, for example, the star expands and there's a companion nearby? Well, the first thing that happens is, okay, you've got a tidal pull from the companion, and so the star is distorted, right? Just like the tides that the moon is raising on the Earth. So you have a star that makes this kind of teardrop shape. Here's its companion star. I am imagining that I'm in a co-rotating reference frame. Of course, both of these guys are moving in an orbit, so I'm shifting into a co-rotating reference frame. So you've got this tidal bulge on the star pointing towards its companion. And at some point, if the star continues to expand, you can draw an equipotential surface in this co-rotating reference frame, which looks something like this. Of course, in here, the equipotential surfaces are mostly circular. But if you, at some point, there is an equipotential surface that goes through a Lagrange point, right? And if this, you can consider sort of what is the volume of this equipotential teardrop that goes through the Lagrange point. And if the star gets to be larger than this volume, then obviously there's some material from the star that just gets removed. Some of that removed material might end up on the companion. Some of that removed material might just be ejected into outer space. This surface has a name. It's called the Roche lobe. But it really is just an equipotential surface. And the act of overfilling the Roche lobe and transferring mass onto the companion is referred to as Roche lobe overflow. So what happens when I transfer mass? Well, let's first consider the case where I am transferring mass completely conservatively. So completely conservatively means every unit of mass that leaves the donor ends up on the accretor. So conservative mass transfer means mass stays in the binary, just goes from donor to accretor, right? So here, this is the donor. This is the accretor. If your mass transfer is completely conservative and all the mass goes from donor to accretor, then what happens to the orbit of the binary is very simple to compute because it just depends on conservation of angular momentum. So suppose the donor is much more massive than the accretor. So I'm a really massive donor. Here's a little low mass accretor moving around me. Because I'm so massive, in this binary, I'm basically sitting in place while the low mass accretor is zooming around me. So that means the specific angular momentum per unit mass is much higher on the accretor than on the donor. So if donor is more massive, specific angular momentum is per unit mass is much higher on the accretor. So if I take a little hair from my beard and move it over here, right, that means I've increased the angular momentum of this hair. So I've added somehow angular momentum to the system, but angular momentum has to be conserved, so I have to remove angular momentum somewhere else. And the only way I can remove angular momentum is by bringing this guy closer together. Because the angular momentum in a binary goes as the square root of the binary's radius, at least in an extreme mass ratio binary, right? Does that make sense? Sorry, maybe I should. Okay. Sure. So I'm for the purpose of doing this hand. Of course, you can do this correctly with the center of mass moving. For the purpose of the hand wave explanation, I'm assuming an extreme mass ratio. So my donor is almost sitting at the center of mass. I mean, the center of mass itself is. I mean, the donor, of course, is moving a little bit relative to the center of mass, but you know, because the accretor is moving much more rapidly, and of course we know that the angular momentum goes as r cross v, right? We know that the angular momentum per unit mass is all at the accretor. Specific angular momentum is much higher than the accretor if the donor is more massive, right? So if I think of a really extreme mass ratio, so I've got a big mass here and a little mass here at radius r, right? Okay, the velocity is proportional to root g, the velocity of this little guy is proportional to root gm over r, and so the specific angular momentum, L, or L over little m, which goes as r cross v, is going to scale as root is proportional to root capital M times lowercase r. So specific angular momentum goes as root r, right? And the fact that specific angular momentum goes as root r means that the wider the binary is, the more angular momentum it has. The closer together it is, the less angular momentum it has. So if I want to remove angular momentum from the binary's orbit to compensate for the fact that, remember, I just gave this hair a bit of extra angular momentum by transferring it onto the low mass accretor, the binary has to shrink. So mass transfer from heavy to light, conservative mass transfer from heavy to light, shrinks the binary. Conservative mass transfer, remember, conservative means all the mass from the donor ends up in the accretor. Conservative mass transfer, heavy to light, shrinks binary. You can probably guess what happens if I go from light to heavy. It does the opposite, right? So now if I take a little bit of mass from this light guy over here, which has a lot of specific angular momentum, and transfer some of it back to me, I'm the heavy one. I have very little specific angular momentum. I've removed angular momentum from this bit of mass by carrying out this mass transfer. The total angular momentum in the system has to stay constant, so I have to add angular momentum somewhere else. The way I add angular momentum is by increasing the binary's orbital separation, because then, since angular momentum scales as root r, that makes the binary wider. So light to heavy widens binary. Why is this important? Well, for example, it tells you that mass transfer light to heavy is in general always stable. You can just keep doing it and doing it and doing it. It widens the binary, and then, for example, if your light guy ends up expanding over time, because, for example, it's still undergoing some nuclear processes, and typically as stars age, as we've just said, the star expands, right? So you start the mass transfer from a light guy onto a heavy guy. That light guy moves out. It disengages from mass transfer for a bit. Then you it expands, it re-engages in mass transfer, that makes it move out even further, it disengages again, and this process can continue. And this, for example, if people have heard about black widow pulsars or redback pulsars, right? This is, for example, the process that is going on, where you have a neutron star and a low mass companion, and the low mass companion donates a bit of mass, moves out, donates a bit of mass, moves out, expands, donates a bit of mass, moves out, and the process essentially continues until there's almost nothing left for this low mass object, and so you end up with a single pulsar sitting there, but you know that it had mass transfer onto it because it's recycled, so that means that it was accreting at some point, except there's nothing that you can see that it was accreting from, and so you conclude that it must have been a case of stable mass transfer from a low mass companion that fed this pulsar. Or in some cases you still see a companion, but it's a very, very low mass companion that looks like it has actually lost a lot of mass, and that's your redback pulsar. So, okay, light to heavy always is stable. Heavy to light may not be stable, and we'll get back to what it means for it not to be stable in a moment. But the not stable part, right? Okay, naively, right? We're almost there in understanding what it means for mass transfer to be not stable, right? Remember, if I go heavy to light, I shrink the binary. Now, in general, if I shrink the binary, the size of the Roche lobe also shrinks. Because, okay, if the mass ratio stayed the same, which of course it doesn't quite because I'm also changing other things in the process. If I'm transferring heavy to light, I'm adding mass onto the light object, removing mass from the heavy object, etc. But you can see that the size of the Roche lobe is going to shrink because basically for a fixed mass ratio, the Roche lobe size is just proportional to the binary separation. So I shrink the Roche lobe, and now the question is, what happens to my star? My star has lost some mass, so you might think, well, if a star loses mass, it surely must shrink. Actually, even that is not always true. So for instance, for a white dwarf, for a degenerate object, that's not true. A white dwarf, the lower its mass, the bigger it is in radius. But for a normal star, typically, yes, it's true, a non-degenerate star, that if it's lighter, it's if you remove mass from it, it will shrink. But the question is, how rapidly does it shrink? Does it shrink as faster than its Roche lobe is going to shrink, or does it shrink slower than its Roche lobe shrinks? If it shrinks slower than its Roche lobe shrinks, that means as I transfer mass, I am only going to overflow my Roche lobe by an ever larger amount, which means I want to transfer even more mass. And then I transfer that mass, and I overflow my Roche lobe by even more, so I want to transfer even more mass, even faster. And this is a runaway process. It's an unstable process. And so, hello. And maybe he was interested too. We shouldn't expel audience members. maybe that was a question. I just didn't understand the question. Okay, so you can have this runaway process of unstable mass transfer. Now, what happens if I have this runaway mass transfer onto a companion? Well, if I have this runaway mass transfer onto a companion, and I do this at an ever-increasing rate, okay, at some point the companion just cannot accept all of this mass. There's only so much mass that a star can process. You cannot sort of feed somebody out of a fire hose, right? So this mass no longer ends up on the star as part of the star. It ends up as a cloud of gas surrounding the binary. So you have this cloud or envelope of gas surrounding the entire binary that happens as a result of dynamically unstable mass transfer. So what happens now? Now I've got, let's say that this happens during a phase where one of my companions is already a black hole, and the other one, or a neutron star, and the other one is still a normal star that's, you know, somewhere on its way up into the giant phase. So right here, I have on the left a black hole. On the right, I have the star, which consists of a stellar core and an envelope. this envelope gets stripped off, and you actually have the situation where this envelope surrounds the entire binary. So now I've got a binary consisting of a black hole and this compact core of the star, let's say helium core of this donor star, that are orbiting each other inside a dense gaseous envelope. Well, what do you think would happen? Well, for one thing, there's going to be quite a bit of friction against the envelope, right? Just drag. This is going to, of course, dissipate energy from the orbit and put energy into the envelope. You're just literally heating up the gas. And the orbit is shrinking. You might have some accretion, right? Some of the material might end up accreting onto the companions. If there is accretion, there is feedback because energy is released during the accretion. That again is heating up the surrounding gas. So the binary is gradually spiraling in. This binary composed of a black hole in this case and a helium core, they are spiraling in together. And meanwhile, the envelope is getting more and more energy deposited into it. And now two things can happen. Either this process of losing energy, putting it into the envelope, and continuing to spiral in just continues until these two objects merge. Or at some point, you successfully expel the gas envelope. You put so much energy into it that you actually send the entire envelope off to infinity. So this is I think when you're thinking about the Jeans mass, you're mostly thinking about whether I can actually form a star by having a collapse, right? Here, what it really depends on is a couple of things. One is is the envelope, how rapidly you're putting the energy in, and is the envelope able to get rid of this energy in other ways during this time, for example, by radiating it away. Secondly, how quick is this process, and whether this energy is even able to redistribute itself through the envelope, or you are spiraling in and so you're only heating up parts of the envelope, but parts of the envelope just along the stellar tracks. And of course the overall energy balance, right? I mean, you need to put in enough energy to at the very least balance the binding energy of the envelope, right? The envelope has some gravitational binding energy. It's initially, right? I mean, so the very simplest calculation you can do is say, okay, let's suppose initially I know what the binding energy of the envelope was relative to my donor star before the mass transfer even started, right? This envelope had a certain amount of gravitational binding energy. If I just imagine that my energy overall is conserved, and when I send the envelope off to infinity, I send it off without too much kinetic energy, so it just barely makes it to infinity, but by the time it gets to infinity, its velocity is 0. You can just solve this energy balance problem, and that tells you what must be the change in the separation of the binary. By how much must the binary shrink? And that gives you a hint as to what would have to be the binary's orbital separation after this common envelope phase. And you find, not surprisingly, that the post-common envelope orbital separation is typically, just from energy arguments, of order only a few times larger than the radius of the stellar core here. So that means you went from the size, a binary that was the size of this giant, right, which might have been 10 astronomical units, to a binary that is only a few times the size of the stellar core, which is only a few solar radii. So you've had the binary shrink by 2 or 3 orders of magnitude as a result of common envelope ejection, and it happens at almost by construction at just the right time, right? It happens at just the right time in the sense that you are getting this common envelope phase right when one of your companions here is already a compact object and the other one is just a small stellar core, so you can afford to be close together. There won't be another significant episode of stellar expansion. There won't be any more risk of merger of the two binaries before you actually have two compact objects and can merge through gravitational wave emission. Now, of course, this requires some fine-tuning, right? What do you need to have happen? Well, you need to have two stars that are massive enough to form. Yes, please. To go supernova. It will, absolutely. Sure, but actually this kick isn't typically as much of an issue because so kicks in general can be a problem, right? Natal kicks during supernova can be a problem because natal kicks, if they're high enough, can disrupt the binary. But in order for a kick to be high enough to disrupt the binary, the kick velocity has to be at least of order the orbital velocity. If I'm moving in an orbit and my orbital velocity is 600 kilometers per second and I get a kick of 1 kilometer per second, it's not going to do much to the orbit. It'll make it slightly eccentric, very slightly, right? So we need to have kicks that are of order the orbital velocity. At the end of the common envelope phase, your binary is already so close together that even a kick of a few hundred kilometers per second is going to be less than the orbital velocity of the binary. So it's very unlikely to be disrupted. The first kick is much more of an issue. When this binary here, which is still a wide binary, the primary collapses. When the primary collapses into a compact object, there you've got a potential problem because this kick can very likely disrupt the binary. Now, one of the questions is, do black holes ever get big kicks? So neutron stars, we know observationally get big kicks. We can see single pulsars moving around with proper velocities of several hundred kilometers per second. We can see double neutron star systems like the famous Hulse-Taylor binary with a significant eccentricity. So the Hulse-Taylor binary, pulsar 1913 plus 16, has an eccentricity of about 0.6, a little bit more than that. That tells you that there must have been a kick, although actually it doesn't tell you necessarily that there was a supernova kick, that alone. Let me explain that for a moment. So suppose I have a completely spherically symmetric supernova explosion in the reference frame of the moving object, of course, right? So from the point of view of the star, which decides to explode supernova, supernova is completely spherically symmetric. But this star was moving in an orbit around its companion, right? So that means if I now look from the point of view of an external observer, or the center of mass of the binary, let's say the center of mass was fixed in the reference frame of my external observer, for simplicity, the ejected material actually carries a net momentum with it. Because yes, it was exploding spherically symmetrically, the star, but it was exploding spherically symmetrically while moving, and so all of this material had a net velocity in this direction. So now there's a net momentum associated with the ejected material ejected during the explosion. That does two things. One is it kicks the entire binary, even if the binary survives, it kicks the entire binary in the opposite direction. But secondly, this sudden removal of material can actually give the binary a significant eccentricity. You can just do a calculation of conservation of energy and conservation of angular momentum of this binary and figure out what would happen. In fact, a fun calculation to do, you can consider this a homework problem before this evening if you have time for it, since we have another lecture this evening, is to ask yourself how much mass as a fraction of the total binary's mass do I need to lose in one single instantaneous explosion, no kick, spherically symmetrical, in the reference frame of the object removing the mass, in order for the binary to become unbound. So for example, okay, if you imagine, I know the sun won't go supernova, but imagine the sun went supernova, and imagine it had a perfectly spherically symmetrical explosion. What fraction of the sun's mass would have to be removed in the spherically symmetrical explosion in order for the Earth to become unbound from the sun? Okay, sure. So what I was trying to say just now is that if you, and I didn't do the calculation, so I'm stating this, but if you remove, if you remove mass from, quickly remove mass from one of the companions in an orbiting binary, from the reference frame of the center of mass, if that mass is not being removed isotropically, it's being removed with a net momentum, And the fact that you're removing it with a net momentum can change the binary's orbital properties. And I'm claiming that there is a threshold where if you remove more than a certain fraction of the total mass of the binary in one instantaneous explosion, even if it's spherically symmetrical in the reference frame of the exploding object, then the binary will fly apart. It becomes unbound. And I'm asking, what is that fraction? So what fraction? Consider the Earth-Sun binary. Imagine, okay, that's a simpler example because you don't have to, you can almost ignore the mass of the Earth in this calculation. You can imagine that the mass of the binary and the mass of the sun are the same thing, right? What fraction of the sun would have to be removed in a pretend supernova? I'm pretending the sun will not explode in a supernova, don't worry. But if you pretend the sun could, then what fraction of the solar mass would have to be removed during the supernova in order for the Sun-Earth binary to become unbound? Okay, so yes, please. So in principle, it can happen in the first stage of mass transfer. We actually don't want it to happen there, because if it happens in the first stage of mass transfer, the binary will be brought closer together, but then when the secondary expands, you will have a merger. Because at that point, the secondary will still expand, right? Primary expands first, secondary expands later. The more massive the star is, the faster it evolves. So then when this guy expands, you have yourself a problem. So what that typically means is there is a particular range of mass ratios you want. Usually, in order to have, so you need to have two things in order to have dynamically unstable mass transfer. The first one is you actually want the mass transfer to be as non-conservative as possible. It turns out that if you remove mass from the binary altogether, you shrink things even faster. It's good to transfer mass onto a black hole in that case, because a black hole's mass capture rate is basically limited by the Eddington limit. And so that means it's not going to capture a lot of mass, so that mass transfer will be almost completely non-conservative. And the second thing is that when you transfer mass here, right, if for example your primary was 10 times more mass than the secondary, then yes, most likely the very first episode of mass transfer would be dynamically unstable. You would probably just end up with a direct merger at that point, because your secondary is still quite sizable in radius. Or if you don't immediately end up with a direct merger, if you really do end up just shrinking the binary a lot, you have this other problem that when the secondary expands, at that point you will surely end up in a merger. If, on the other hand, you're transferring mass here, so at this point, if for instance initially my masses were comparable, and so my first episode of mass transfer was stable, no common envelope phase, then during the second episode of mass transfer, you end up naturally with a mass ratio of something like 3 to 1 or 4 to 1. Why? Well, because first of all, you transfer some mass from the primary onto the secondary, so your secondary actually at this point is more massive than the primary anyway. And also, the black hole only ends up being something like a third of the mass of the star, because most of the mass is never processed. It just sits around as hydrogen on the outside of the star, or in this case, if you already had a mass transfer episode, that hydrogen was removed anyway. So this thing is only maybe a third or less of the mass of the original star. This is actually more than the mass of the original secondary. So you maybe have a mass ratio of something like 4 to 1, and that's just about the right ballpark to have a common envelope phase, dynamically unstable common envelope phase, if you have non-conservative mass transfer. So it's natural for this to happen, at least in some cases in this order. It can happen in a different way, but then those things will not give you double compact objects. And so this is where the fine-tuning comes in. You need to have a particular range of masses, a particular range of orbital separations, a particular range of mass ratios, and given that I'm now at time, we'll talk about what those have to be, as well as discuss the other channels this evening. Thanks.